Okay, so we are going to start with question number 4, part A. Cobalt 2 nitrate, and we have a formula, is a reddish brown crystalline solid. Okay, it dissolves in water to form a solution of containing hexa aqua cobalt 2 complex ions. Complete table 4.1 giving the formula of the cobalt containing species that is formed in each of the 3 reactions described. So if you recall, the reactions is exactly going to be the same as when we add these reagents with the copper complexes that we have studied in the classes. So if you recall, with the hydroxide, only two of the, hydroxide displaces two of the water out of these six. So it is going to be, the formula would be like this. And as cobalt is 2 positive and a hydroxide ion is -1, so as a result, the net charge is going to be 0 in this case. So 4 water molecules and then no net charge. Okay. And excess of ammonia. Okay. So when we use excess of ammonia in cobalt, all of the water molecules displaced by the excess of ammonia. In copper, and it's a aqueous ammonia. In copper, with aqueous ammonia, 2 water molecules stays, and there are 4 ammonia molecules which are present in the complex. But with cobalt, aqueous when we, which one, Abdullah? When we use with aqueous ammonia, all 6 water molecules displaces. In this one, whenever we use a hydroxide, whether it's a cobalt or it's a copper or any other, only 2 of the water molecules as a ligand displaces by the 2 hydroxide ligands. And see, as the charge is 2 plus of a cobalt because water has a no charge. So when 2 hydroxide ions gets bonded, the net charge becomes 0. An excess of concentrated hydrochloric acid. So chloride is the size of a chloride is big. So we will get COCl4, only 4 chloride ions bonds as a ligand in the complex, and the charge would be 2 negative. Is this clear to all of you? Yes, is it clear to all of you? Okay, now part 2. Describe the color changes seen in reaction 3. If you see the reaction 3, in reaction 3, the original color of cobalt is, you recall, it's pink. And the final color after addition of an excess of concentrated hydrochloric acid, the color changes to blue. Maveen, are you asking about this one? Yellow is with a copper. And in a copper, when it's a copper over here, then instead of this color, it's a blue. And when chloride complex of copper is formed, it's yellow. Okay, Shahan? But when there is a cobalt, so the cobalt, we got pink, and here we got blue. Okay, just give me a minute, please. Yes, am I audible right now? Okay. Yeah, there is a disconnectivity. I hope now my screen is shared as well. So, yes, Mahavi, when we use aqueous ammonia and there is a cobalt complex, then in this case, all of the water molecules are displaced and we got the ammonia present and only ammonia, 6 ammonia ligands are present in the complex. Is it clear? Okay. But if, for example, instead of cobalt, we have a copper. So now is it working properly, my screen? No, it's again lagging. Okay, so what I was telling, if there is a copper complex and we are using aqueous ammonia, then in this case, with excess aqueous ammonia, we usually get this complex where there are 4 ammonia molecules and 2 water molecules in the complex, if we use aqueous ammonia. But with the copper complex, if there is a liquid ammonia is used, then the complex form has all 6 ammonia ligands in the complex. But with the cobalt, aqueous ammonia will give us the 6 ammonia ligand complex. Is this clear? Okay. Now, calcium nitrate is a white crystalline solid. When heated, it start decomposes approximately 500 degrees Celsius. Write an equation for the decomposition of calcium nitrate. So I hope you all know that the decomposition of metal nitrate, when you heat it on decomposing, it turns into metal oxide. Nitrogen dioxide gas has been released and oxygen. To balance this equation, you have to put you need to put 2 over here and half over here. So instead of M, I'm going to use the specific metal like calcium nitrate. So CaNO3 twice on heating gives you calcium oxide plus nitrogen dioxide plus oxygen, and to balance, you have to put 2 and half. Is this clear? Yes. Okay. Now, suggest temperature at which magnesium nitrate and barium nitrate start to decompose. Explain your answer. Okay. So here in this case, if you look at periodic table, you will find that magnesium, then you have a calcium, then you have a strontium, then you have a barium. So when we move down, the ion polarization decreases, and as a result, thermal stability increases, which means that the metal which is at the bottom, when forms a complex, that forms a complex, that forms a compound, would have a higher temperature. Yes, very good, Maham. The magnesium nitrate would have a lower temperature. So temperature at which magnesium nitrate starts to decompose. Uh, So the 500 is the temperature for the calcium nitrate. So obviously it is going to be lower than 500 degrees Celsius. And barium is below calcium and strontium, so it would decompose at a higher temperature. So we will write higher than 500 degrees Celsius. Yes, they ask for the temperature, suggest temperature. They ask a suggestion. So you have to give some value. So as it is decomposing at 500, so magnesium nitrate is going to be decomposed at a temperature obviously lower than 500, and it is going to be a temperature higher than 500. Okay. Now you have to explain. So size of magnesium ion is smaller than calcium ion, and size of barium ion is greater than calcium ion. Larger size cation causes less polarization or less distortion in nitrate. Hence, nitrogen oxygen bonds get stronger. Is this clear to all of you? Notes of enantiomer regarding what you are asking, Muhammad. There are two enantiomer. One is no, because it's an ionic bond. It's the attraction between the opposite charges, not a specific bond between the nitrogen and a metal, Shahan. Okay. It's an AS organic, Muhammad. Now question number 5. Transition elements behave as a catalyst and can form complex ions. Explain why transition elements behave as a catalyst. Uh, it is because they have a variable oxidation state, right? Transition elements have more than one oxidation state and have empty d orbitals. So due to variable oxidation state during the reaction, they can change their oxidation state from initial to an intermediate and then come back to the initial, so they get restored. And due to the empty d orbitals, there they can form dative bond or coordinate covalent bond with ligands. So see in the okay, now part B. Silver forms the linear incomplete D subshell. If you are say, yeah, you can also write incomplete, but see when the dative bond is formed with the dative bond, the ligand donates or share, it's a pair of electron, and for a pair of electron, the d orbital must be vacant or must be empty, right? And as a subshell, it has an incomplete d subshell. But as a orbital, they do have a vacant orbital, empty orbital. That's why they are able to form the dative bond. For a ligand, it's because they have just a lone pair, because they share their lone pair. They can share the lone pair to the transition metal, so that's why they are ligands. Silver forms a linear complex with iron. Okay, this is the formula. Copper forms a tetrahedral complex ion. Titanium forms a complex, okay, where diers is a neutral bidentate ligand. State the oxidation state and the coordination number of titanium in this. Okay, as they have told you that it's a bidentate ligands, it means it is forming two bonds. So how many of these ligands are there? Two, which means they are going to form four bonds, and there are four chloride, and the net charge is 0. We know chloride has a -1 charge, so there are four chloride, which makes it -4. And if it's -4, the net charge is 0, then it means titanium must have a +4 oxidation number. So the oxidation number is +4, and the coordination number, if you see, there are four chloride. So each chloride is making one dative bond. So four dative bonds are formed by four chloride, and four dative bonds are formed by these two diads. So the total number of dative bonds are 8. So the coordination number would be 8. Is this clear? Yes, 1 minute. See, it's TiCl4 diers 2, right? So it is forming four bonds, because they have told you that it's a bidentate ligand, which means it forms two bonds, but there are two dier, which means they can form four bonds. There are four chlorine, which means they are also forming four bonds, because one chlorine forms one bond. So the total number of dative bonds would be 8. So the coordination number is 8. Is this clear? Now, they have told you about dier that it's a neutral. So the charge is 0. There is a no net charge, so it's 0. We know chlorine has a -1 charge, and there are four chloride. So -4. So it means titanium must have a +4 oxidation number. Now is it clear? Okay. Draw three-dimensional diagrams to show the shape of AgCN2. If you see, they have mentioned it's a linear. And for this one, they have mentioned it's tetrahedral. Right? Okay. So, and label one bond angle. Okay. So with AG, as it's a linear, so you are going to put a two horizontal lines and put a CN on both the sides. and the bond angle is 180 in this case. With the copper, as it's a tetrahedral, and they ask you to draw the three-dimensional, right? So you will put two bonds on the plane, which are with the symbol lines. Yes, Mariam, what you want to ask? One bond with the, okay, bond on the plane and one bond below the plane. So there are four CN. So one CN, second CN, third CN, fourth CN, enclose in square bracket with the -4, and we know in this case it's a tetrahedral, so the bond angle would be 109.5 degrees. You have to keep in mind the above the bond plane, the bond above the plane and the bond below the plane must be adjacent to each other. There is no normal bond between these two. Yeah, it's -1. Thank you, Shahan. Which charge is -3, Mariam? Yeah, my bad. It's -3. Sorry. You have to go through the notes, Sana. We have discussed that which kind of ligands can form tetrahedral and which kind of ligands can form uh, square planar. Okay. Now next part. The numerical value of the stability constant of copper 1 complex is this. Okay. Write an expression for the K step of this. Okay. So if they are asking for this complex, no, we studied it in transition metals only. Okay. So it means that all the complex are formed when we have a hexa ion. So it means the equation would be like this for this K step, that this was the initial complex we has when we dissolve copper in water, any copper compound in water, and then four cyanide ions reacts, and as a result, we got this, and six water molecules are displaced. Is this understandable? Now, after this, when you are writing the K step expression, remember these water molecules which are displaced from the complex are not written in K step expression. And the rest of the things are same, that the concentration of a product divided by concentration of the reactants. So the concentration of the product would be, product is complex CuCN four 3 minus divided by CuH2O 6 2 plus, and then cyanidine raised to the power 4. Yeah, because it's a concentration, right? In case step, we use the concentration, and concentration is also is for the solutions, Maham. And Abdullah, you will find it in a transition metals chapter. Now, part 2. In a solution, the concentration of cyanidine and this complex are both 0.01001 mole per dm³. Use your expression in C1 and the value of K step to calculate the concentration of copper +1 ions in this solution. Okay. So the concentration of copper plus one. Okay, there is a one important thing over here that I have missed. See, it's a copper one complex, right? So it means it's not going to be copper 2 plus, it's going to be copper plus 1. Okay. And in the same way here, it is going to be copper plus 1. So remember that whether you write CuH2O 6 2 plus, let's suppose, or Cu plus, both are the same thing. So they ask you to find the concentration of copper. So if you write the K-step expression again, let me rewrite it, that this ion is in the product, so it's in denominator, divided by copper plus 1 ions times cyanide ions raised to the power 4. And they have told you the concentration of both cyanide and this complex are same, right? And we got the K step value, which is over here, 2 exponent minus 2 exponent 27. So 2 exponent 27 is equals to 0.0010 over concentration of copper ions times 0.0010 raised to the power 4. No, these two are not same. In terms of oxidation number, they are two different species. So the concentration of copper 1 positive is going to be 2.0 exponent 27 multiplied by 0.001 raised to the power 4 divided by 0.0010. Can anyone calculate it and tell me the answer? Shahan, 2 positive ion and 1 positive ion are obviously has a different oxidation state, so they are going to be considered as a different species, okay? So the answer is 5.0 exponent minus 19. Abdullah, the best way uh, is that just read the question, and if you are going to attempt it readily without spending a time on thinking, do those parts first and then move ahead in the paper till the end and then continue from the start. In that way, you are able to manage the time. Otherwise, if since from the first question, if you start spending some time on thinking on every question, then at the end you will left with the paper. So always just read the paper, read the part, and if you know that yes, you can do it right now, so do that, then move to the next part. And if you think that you have to need some time to think over that part, so just leave it and look for those parts which you can do it readily. Okay. Now, B part. A piece of copper containing alloy has a mass of 0.567 gram and it is dissolved in acid giving 100 centimeter cube of a blue solution in which all the copper present is Cu2 positive ion. Okay. So 0.567 gram is a copper alloy in which copper is 2 positive and it is dissolved in 100 centimeter cube solution which gets blue in color. Okay. An excess of potassium iodide is added to a 25 centimeter cube sample of this solution. So it means from this 25 centimeter cube is taken out And in this 25 centimeter cube, excess of potassium iodide has been added. And when this added, this reaction would occur. Is this clear to all of you? And here they said that all of the copper is precipitated as a white CuI. Copper 2 positive ions are the only components in the solution that react with potassium iodide. This is reaction 1. Okay. Now, the liberated iodine, which is formed over here, is then titrated with thiosulfate. This is reaction 2. So it means when this has been added, we got iodine over here. And in that iodine, we have added thiosulfate, S2O32 negative. And when we add this reaction would occur. Is this clear? Okay. Then they are saying the titration requires 20.10 centimeter cube of 0.02 mole per day to reach the endpoint. Okay, calculate the number of moles of iodine that are reduced in this titration. So it means they are asking about these moles in part 1. Okay, so if I got the moles of thiosulfate, because I know its concentration and its volume, I divide it with the 2 to get the moles of iodine because the ratio is 2:1. So it means first I will find the moles of thiosulfate, and for the moles of thiosulfate, I know its concentration, which is 0.0200 times its volume, which is in centimeter cube. So I have to divide it with 1000. So I'm going to get the moles of thiosulfate. Can anyone calculate the moles of thiosulfate and tell me the answer, please? Okay, it's 4.02 exponent minus 4, right? So these are the moles of thiosulfate. And if you look at the ratio, it's 2:1. So it means for moles of iodide, I have to divide these moles with 2, right? Because the ratio is 2:1. So if I divide it with 2, I will get 2.01 exponent minus 4, the moles of iodide. Is this clear to all of you? For this one, you can do it like this. Moles of thiosulfate is 2 moles of iodide. There are 2 and there are 1. This ratio we got from the balanced equation from here. And then 4.02 is 2x. Okay. Now, what they are saying, calculate the number of moles of copper in the original piece of alloy. So if you see, you got these moles of iodine which are here, and they actually came from here. So if I take the ratio of this equation, I am able to find the moles of copper ions, but these moles of copper ion in how much volume of copper? 25 centimeter cube. Because if you see, we have taken 25 centimeter cube and in which potassium iodide is added. Is this understandable? Yes, the moles concept is same. So if we take the ratio from this, these are the moles of iodine which are formed from these moles of copper ions. So the ratio would be iodine is to copper 2 plus ion, and it is 1 mole of iodine is produced by 2 moles of copper. So if we have these moles of iodine, then the moles of copper would be x, and if you calculate the value of x, you will get 4.02 exponent minus 4 moles of copper to positive ions. But these moles are in 25 centimeter cube. Why? Because if you see this summary, that we dissolved this in 100 centimeter cube of solution, and from this 100 centimeter cube, we took 25 centimeter cube, and then we have added potassium iodide. So the moles we got here in 25 centimeter cube, and they ask you in in the original piece of alloy. So in the original piece of alloy, whatever the moles, these are the moles which are present in 100 centimeter cube. So I will make another ratio that 25 centimeter cube solution contains 4.02 exponent minus 4 moles. So if the volume is 100 centimeter cube, then there would be X number of moles. So if you calculate the value of X, it is going to be times 4. So if you go multiply it times 4, it is going to be 1.608 exponent minus 3. Can anyone confirm me the calculation, please? Okay. Now what they are saying, calculate the percentage of copper in the alloy. So we got the moles of copper. So the mass of copper would be equal to moles of copper multiplied by its AR. So the moles of copper are 1.608 exponent minus 3 multiplied by its AR. Can anyone confirm me its AR? I think it's 63.5. You got the mass of copper. Yes, what mass of copper we got? 0.0255, right? This is the mass of copper. The mass of alloy is, if you see, 0.567 grams. So this is the mass of pure copper in the in this mass of alloy. You have to times it 100 to get the percentage. Rahan, I think your calculation is not correct. Can you check it again? And it's exponent minus 3. Can anyone check me this answer at 0.0255? I am doubtful it's wrong. 63.5 times 1.608 exponent minus 3. Shahan, can you verify this again? Okay, it's 0.1021. Okay, it's 0.102. So 0.102. Now, I think it's 18%. Thank you, Aliyasat. Till here, is this clear to all of you? Okay. Now, suggest why a solution of Cu2 positive is colored, but solid CuI is not colored. Now, see, it's a concept-based question, because if you see here, copper is 2 positive, and in copper, when the copper is 2 positive, in its d orbital, there are 9 electrons. But if you see in CuI, the copper is 1 positive, and in 1 positive, it's d10. No, Maham, the thing is that when it's a d10, the d orbitals is splitted, but there is a no space for the electron to jump from the lower to higher because all the orbitals are completely filled. So if no electron can gain the energy, can absorb the visible light, so that's why there will be no color. So it is transmitting the whole light, not absorbing any energy. So in Cu2 positive, it's D9, D subshell is not full, hence DD transition means from the lower energy to higher energy of electron is possible. Yeah, obviously that's why how otherwise how you justify. The simple thing is that when the transition element is showing the color, it means that its d orbital is basically not full. There is a space for the electron, and that's why when the d orbitals split into two levels, the electron from the lower energy can jump to the higher energy, and as a result it absorbs some radiation and trans and rest of them is is transited. So as a result, we have observed the color. But when the d orbital of a transition metal ion is completely filled, then after the splitting, there is no space in the higher orbital that the electron from the lower orbital can jump to the higher orbital and gain the light from the visible region. So as a result, it stays white. Is this clear? So D subshell is completely filled, hence DD transition of electron is not possible. Is this understandable to all of you? Now, question number 6a. Five ligands are listed in table 6.1. Ammonia. So in ammonia, there is a one atom, so it's a monodentate. EDTA, if you recall, mentioned in a note, it's a hexadentate. CN is a monodentate ligand. And C2O4 2 negative, it's a oxalate ion. It's a bidentate ligand. Yeah, DD transition mean that the d orbitals are like this. When the ligand approaches, the d orbitals split it like this. So the electron can jump from here to the higher energy d orbital, and as a result, it absorbs energy, and the rest of the energy is transmitted, and as a result, the color is shown. But when it's a D10, so see in D10, there are 6 electrons over here and 10 electrons over here, 4 electrons over here. So there is a no space for any electron which can jump from here to here. So as a result, it stays white. But in D9, see, this one has a space for, sorry, this one has a space, oops, this one has a space for, this one has a space for one electron. So one electron can absorb energy or absorb a photon and jumps to this. So when it absorbs a photon and transmit the rest of the one, so the color can be shown. Is it clear now? Yes, Abdullah, did you understand? Okay, Mahmeen. Okay. Now, complete table 6.1 using the word. Okay, we are done with that. Okay, so they are ask you to write polydentate. So here you can write polydentate, not hexadentate. Okay. Each of these, okay. The molecule is a tridentate ligand. Suggest the meaning of a tridentate. So I think it's very easy. That tri means three. So it can donate three or share three lone pair of electrons with transition metal ion. Polydentate means it can form multiple dative bonds, more than two. Suggest how it acts as a tridentate ligand. So it has three nitrogen atoms and each nitrogen has one lone pair of electron. Okay. Now, nickel forms a octahedral complex. This complex can exist in three isomeric form listed in table 6.2. One of the form is a trans isomer, the other forms are two different cis isomers. Complete table 6.1 using term polar and non-polar. Okay, so the trans is the one in which the water molecule, for example, let me do it like this. See, the trans one is the one where we got the water molecules over here. And En is a bidentate ligand, so one En over here and one En over here. So the exactly same groups are exactly opposite to each other, making it non-polar. And in cis, remember, when there are different groups, but as a trans, it is making non-polar. So remember, the cis is always polar in that case. So these are going to be considered as a polar. Okay. Now, describe the difference between cis isomer 1 and cis isomer 2. So it's very easy if there are two cis isomers. So if you see this one, this is a trans, right? So in the trans, the same groups are exactly opposite to each other. So there is a no charge distribution because both the sides have a same charge. So that's why it becomes non-polar. Now, if I draw the trans, for example, so if I draw the cis, let's suppose like this. So one H2O is over here, and let's suppose the other H2O is over here. So we got one En over here and one En over here. So see. Okay. Let me share it again. Now, is it visible to you guys? Now look over here. In this, there are two water molecules which are exactly opposite, and the two En molecules which are exactly opposite. So these two sides have a same charge. And in the same way, these two sides have a same charge. So there would be no partial, if it's, for example, partial negative, so it is also going to be partial negative. So see, there would be no charge distribution and no pole. So that's why this is a trans which is going to be considered as non-polar. Is this clear now? Now, in this case, if you see the two water molecules are at 90 degree to each other and they got the same charge. So obviously their electronegativity difference is, different than each other. So one side becomes partial negative and the other side becomes partial positive, making it polar. Yes. Yes, that's what I have said initially, that the trans one is always a polar, non-polar, and the cis one is also polar. Now they are asking the difference between the two cis. So what would be the difference? The other difference is that if you will make its mirror image, so it is also going to be a cis. Like this, if I make it like this, H2O, H2O. So one EN over here and one EN over here. So see, it is also a cis and these two are mirror images of each other. So the difference is over here that they are optical isomers. And what is the difference between the optical isomers? The actual difference is that they rotate plane polarized light in different manner. Is this clear? Yeah. The other difference is that they are non-superimposable to each other. The other difference is that both the optical isomers or the enantiomers have a different medicinal activity. One is releasing the pain, the other one is causing the side effect. That's what we have studied in chirality. Is it clear to all of you? Okay. So we are left with the 3 questions, and tomorrow we are going to complete this paper. And then on Saturday, inshallah, we are going to start the February, March, February, March 2024 paper. Okay. So see you everyone in the next class. Take care. Goodbye and Allah Hafiz.